20-foot runway is necessary to give a takeoff for this man-operated machine of the air. And defying death, the intrepid inventor himself sits at the controls and hurls himself into the sky.
Man's attempts to copy the birds have traditionally failed, because his body has not such an efficient weight-to-power ratio. He had to wait for the internal combustion engine, which was comparatively light, but which could put out as much as 15 or 20 horsepower. People still weren't satisfied, though. They no longer believed the doctor's ancient and gloomy predictions that the body would disintegrate at speeds over 50 miles an hour. Instead, they wanted to go faster and faster. This, and the demands of the Second World War, pushed piston engine and airframe development to their limits. Piston-engined aircraft were beginning to approach speeds of 500 miles per hour. Speeds above this, however, presented new problems. In the search for greater speed, the engines became heavy, putting great stress on the airframe, and the speed of the propeller, especially at the tip, became so fast that it was starting to become counterproductive. It was creating a lot of turbulence, but no real thrust. If man was to go faster, he needed to look for a new and more powerful engine, which didn't need a propeller: the jet engine. In this program, we'll be looking at the principles of the jet engine and trying to answer basic questions such as how does it work and what's it used for. But first of all, what is a jet engine? In the simplest terms, the squid is nature's jet engine. All the squid does is suck in water slowly and push it out again at a higher speed. The act of forcing the jet of water out in one direction propels the squid in the opposite direction. This is known as jet propulsion, and is explained in Newton's third law of motion, which states that every action has an equal and opposite reaction. The same principle of jet propulsion can be seen with a child's balloon. Here, of course, air is used, and not water, but air and water have similar dynamic properties, and the same principles apply. First, air is forced into the balloon. When the balloon is released, the tension in the rubber pushes the air back out through the nozzle at high speed. Designed by Sir Frank Whittle, this was the first successful jet aero engine. From it came a whole new generation of engines, some of which are still in operation today. And even now, the basic layout can be used to explain how a modern jet operates. The engine can be split up into four main areas: compressor, combustion, the turbine, and the exhaust. The compressor has two jobs. It draws air in from outside, and it also compresses the air. Some of the air is forced into the combustion chamber at very high pressures, so that when the air and fuel are mixed together and ignited, a rapid increase in heat energy is produced. This occurs in the combustion chamber, from where the burned mixture of air and fuel is sent rushing at high speed into the turbine. As this gas expands, part of the energy is used to power the turbine, which in turn drives the compressors. Finally, the gas is directed out through the exhaust nozzle. It's lost energy through the turbine, but has accelerated through the nozzle, and provides the propelling jet stream out of the back of the engine, and therefore, by reaction, thrusting the engine forwards. This is the whole point of the operation: taking air in at normal speed and forcing it out at a higher speed, backwards, thus sending the engine forwards. It's important to remember that these individual stages form a complete and continuous working cycle. A constant generation of power. All the sections of the engine are designed to make the flow of air through the engine as efficient as possible. The compressor does this by having both rotating and stationary blades, or rotor and stator blades. The rotor blades take the air and force it backwards through the engine, while the stator blades channel the air so that it hits the next series of rotor blades as cleanly as possible. As the air is pushed through the compressor, the space available for it is reduced, and it gets literally packed in. So much so that compression ratios of 30-to-1 are possible. The compressor is driven by the turbine. One turbine can drive the whole compressor, but now there are often 2 or 3 turbines in an engine, each with a separate shaft that rotates a different section of the compressor. The fact that the sections can then rotate at different speeds means it's easier to maintain the correct overall flow of air through the engine, and the entire engine can be made shorter and stiffer. When the air reaches the combustion chamber, it's at a pressure of up to 450 pounds per square inch and is travelling at more than half the speed of sound. Fuel is difficult to burn under these conditions, and so a combustion chamber provides the correct environment, an area of more slowly moving and swirling air that is sprayed with fuel. This mixture will ignite, and the increase in heat energy is quite considerable. The burning gas can be as hot as 2,000 degrees centigrade, and at this sort of temperature, the metal the turbine blades are made of will melt. However, the influx of colder air that had not been taken through the combustion chamber, but diverted for cooling purposes, brings the operating conditions in the turbine down to a manageable 1,000 degrees or so. Often, as well as driving the compressor, the turbine will also provide ancillary power, or even drive a propeller. It's vital that turbines are perfectly designed and manufactured. Just this one stage, the high-pressure turbine can generate 50,000 horsepower, at which point the blades will be spinning at 1,500 feet per second. That's over 1,000 miles an hour. So everything must be done to ensure that the passage of the gas through the turbines is as smooth as possible. Similar care is taken as the gas leaves the engine through the propelling nozzle. It's these exhaust gases that provide the thrust to power the engine, so it's essential that they're propelled from the engine at exactly the right speed and pressure. This is largely determined by the size and shape of the propelling nozzle that can give a kick to the gases as they leave the engine. The completed engine is, of course, a vast and complex affair once the noise suppression, cooling, lubrication, electrical, fuel and other systems have all been added. But the 4 sections of the working cycle remain unaltered: the compressor, the combustor, the turbine, and the exhaust. Soon after the invention of the jet engine, it was decided that brute force alone wasn't enough, and designers started to look for ways to develop this newfound source of power. The type of engine that we have been looking at is called the turbojet. It was the first kind of jet to be made, and it remains the best for high speeds as it's very powerful but small, and has a low frontal area, so it can be easily streamlined. The turbojet can be made even more powerful by adding reheat. In this system, fuel is sprayed into the exhaust and lit, so there's a second combustion stage, which provides extra thrust. Reheat is generally used only for short periods, to give extra acceleration, such as on takeoff. On landing, however, deceleration is wanted, and then thrust reversers are used. These are flaps that move to divert the gas forwards rather than backwards through the exhaust. This has the effect of slowing the aircraft down, as the jet reaction tries to propel the engine in the opposite direction to the airflow. A development of the turbojet is the turboprop. This has an extra turbine, which drives a propeller. Aircraft powered by a turboprop are not as fast as those powered by a turbojet, but nevertheless the turboprop remains a very efficient and economical engine. If the propeller is removed from a turboprop, then the resulting engine is called a turboshaft. The shaft is coupled to a gearbox, and through this it can drive a helicopter rotor. Much of the latest development, however, has been done on the turbofan. Here, only some of the air is fed through the compressor and combusted. The rest is partially compressed and is bypassed around the hot core of the engine. This cuts down the engine noise as it reduces the overall speed of the jet stream. An exciting development of the turbofan is vectored thrust. Here, there are 4 nozzles, 2 of which take the bypass air from the fan and 2 take the exhaust gases. The nozzles can swivel through 90 degrees, so they can point down for vertical takeoff and rearwards for normal horizontal flight. The most popular example of vectored thrust is the Pegasus engine that powers the Harrier jump jet. All in all, the jet engine has come a long way since the early days of the 1940s.